Yeah, great. Nice to have everybody here so early in the morning after the party yesterday. I'm Eric. I'm working as a security consultant, mostly do code auditing, pen testing at a small company in Germany. I'm father of a daughter. Why is this on the slide? Because some of the work here was done during work time, some of the work was done at conferences, and some of the work was done when my daughter woke me up at 3 in the morning and I couldn't get back to sleep. So the issues I'm presenting here are not yet told to the developers. I usually don't do this. In this case, it was I was so frustrated with the state of open source IoT security that I did not really care. The exception are the riot bugs. I told them last year, but the ones in those slides are still not fixed. So yeah, figure. I didn't do any fuzzing or yeah, big static analysis, dynamic analysis. I was just reading code. My conclusion from the stuff I have looked at is yeah, basically everybody in the IT world is talking about security, but their understanding of security is completely different from mine. They mostly try to protect from somebody pushing a new firmware on the devices and not from somebody attacking the devices in other ways. So yeah, that's mostly just half of the game. They try to take my freedom away to put another firmware on the device and still don't keep it secure, so I can't even patch it if there's a bug. So that's yeah, nothing I like. I looked at 4 different IoT operating systems. One is Riot. It's yeah, has academic background. There's Minute, which is from the Apache Foundation. There's Contiki, which somebody told me is the IoT project everybody else gets their inspiration from. And there's Zephyr, which is sponsored by the Linux Foundation. So these are not like some one-man projects, but yeah, popular IoT open source projects, right? On what devices do they run? They don't run on your refrigerator where you can or could easily run a Linux, right? They run on tiny devices where memory is a constraint, where processing power is a constraint, sometimes even energy. So they are designed to run on less than 1 megabyte of RAM. If you look at the Linux kernel, you can get it down to 1.5 megabytes. If you apply some tricks, maybe a megabyte. If you do some satanic sacrifices, maybe to half a megabyte. But then it starts to get hard to further reduce it. I guess if you put some time and effort in this, you could get Linux kernel to maybe 300 kilobytes. Those operating systems start at something like 10 kilobytes to 100 kilobytes, so they're way smaller than something you can do with the Linux kernel. What is an IoT OS? Basically, it's the glue between the application you are writing. The platform SDK is like the C compiler, a C library, maybe some drivers, and basically makes it easier for you to program on such an IoT device. A lot of people are writing everything they need from scratch, and the IoT operating systems are there to make stuff more convenient. A bit of history, a friend of mine last year asked me to look at RiotOS because he's working with it. And for me, it was like, now everybody says IoT is insecure, why should I, right? Then I went to a conference in Warsaw and got drunk and still had some beer left. And I did what you were told in the keynote yesterday not to do. I drank and hacked. So I very easily found the first few bugs. So that's when I started to get interested. What do they actually do to keep their stuff secure, right? I found several bugs. I reported them. For me, it was like also a test case to see how good the developers react. Will they publish advisories? Will they publish timely fixes? Yeah, the reaction was yeah, your typical open source reaction, right? they don't have processes to deal with this kind of stuff. I don't think they assigned a CVE ID for any of these issues, so yeah. What does OS programming looks like nowadays? If you look at Windows, if you look at Linux, we have a lot of fuzzing going on. People are trying to harden the operating systems everywhere they can. We have static analysis tools which were used by most most operating systems. Because by now we learned that writing stuff in C is very hard, and it's very hard to do this securely. So I guess after 20 years of pain and time to learn this lesson, the IoT community should have learned something as well, right? Yeah. For none of the projects, there seem to be some kind of audits, like security audits, where they have an organized way of people looking at things. There seems to be some static analysis done. I couldn't get the numbers for the Coverity stuff they're doing. I mean, there's Coverity for the Linux kernel, but very few people actually look at the results, so that doesn't really say anything. There was very few fuzzing going on. For the Riot OS, I looked first at, there was a fuzzer for a file system. When I ran it, I found buffer overflows in the fuzzer itself. So apparently nobody ever really used the fuzzer. For the Minute operating system, there is a fuzzer for the LWIP, the IP stack. Apparently this one gets used. I just ran it for a few hours to see if something pops up fast. Nothing did, so I guess they're kind of okay there. But it's just the IP stack, right? Nothing else. There's no hardening done at all on none of the operating systems, right? There's some stack protection code in SafeOS, but that's it. So on one of the slides earlier, there was a note that there was no memory management unit on most of the devices. So what does an MMU do? It basically allows you to separate memory and to give permissions to different memory regions. If you don't have it, you can't really have separation between different users. So you can't do any sandboxing, you can't do any, you can't do any privilege separation really. This means every bug you have which is exploitable is automatically a complete compromise of the device. So every bug is a complete compromise, you don't have any hardening. That's not how you should develop an operating system nowadays, right? Only SafeOS has some support for an MMU, but only on x86. So, yeah, in most cases, you have a complete compromise once you find one exploitable bug. I scratched this earlier. Most of the time, IoT people think security is about crypto. Just putting some crypto on it will make it secure in a magic way, but no crypto whatsoever will help against the buffer overflow. So one of the things I looked at is how the security is set up. And one part of this is the randomness you need to create session keys, for example. Then you find code like this in the TLS library. DTLS is TLS via UDP. If you're running on one of those systems, they initialize the random number generator with the current time. If you take a basic course in randomness, that's not high entropy, right? Every attacker can guess this. So that's not how you should do it. This basically allows any attacker to break your keys. And then I looked how the random number generator they're using is structured. Yeah, it's falling back on the rand function from the libc, which the man page explicitly states it's a weak pseudo random number generator. So that's nothing even remotely secure. So you could say they fucked up twice. So how do the operating systems itself support the randomness? For Contiki, there's no entropy pool. There's some support for hardware random number generators if your device has it. But if there is none, it falls back to the rand function from glibc or GCC, depending. If you use the hardware random number generator from the NRF chip, it can fail. It can hang forever. So you might need to get randomness and the box hangs. For some other chips, it might return 0 in case of an error. So if an attacker is able to cause this kind of error on the hardware, all your random numbers will be 0. So that's not how you should do it, right? What's in Minute? There are some pools, they have support for that, but I did not find any spot where they add any entropy in those pools. So that's all part of the work for the application developer. There are some unused hardware random number generators, so you can use them, but you have to do it in your application as well. And there are also 2 random number generators for the hardware which can fail, so you won't get any random number when you might need it. Riot, no entropy pool, they only have pseudo random number generators, and the code for the hardware random number generators has to be added by your application as well, right? So this does not actually help the application developer because he still has to do the work which the operating system is supposed to take away from him. For Saphier, the TLS library has a pool, so that looks good on this end. But yeah, they also have fallbacks to time-based pseudo-random number generators. So yeah, it's really no help at all. So what would you want from a developer's perspective? You would want something like DevUrandom. You want to have a pool which provides you with entropy and which cannot fail. So no matter what your current state is, you get some entropy to set up the new connection or whatever you need to do. You need a pseudo-random number generator, which is secure in a cryptographic way, so no attacker is able to predict it or can predict the outcome of the next number from the current state. And you could argue whether you need equivalent, for DevRandom. DevRandom can block and is usually used to produce longer living keys. I think you most probably want to generate the long living keys on an external device and push them on your IoT device. But yeah, you definitely need some support for some DevUrandom kind of interface. What else is there in operating system? What makes life as an application developer easier? Allocators, which help you to get memory. In the IoT world, depending on your threat model, getting memory allocated based on external input might be a bad idea. For example, the LWIP library has pre-allocated buffers. So if there's another packet coming in, it will just discard it if there's not enough memory and will not try to allocate it from some external allocator. So what happens in the IT world, they try to fall back on a lot of code that's coming from the more embedded world, where there's more memory, more processing power. And this code likes malloc and likes to allocate stuff and freeze it and work with memory in a dynamic way. So so the IoT operating systems provide support for this, and or some of them. Contiki avoids the classic malloc, which is good. It has 2 allocators still. The MEMB keeps this metadata out of band, which is always a good idea, because then if some memory overflow happens, you can't play tricks by abusing the allocator itself. But it's using a continuous block of memory, and there are no overflow checks, right? So if you can overwrite a block of memory, chances are that you will write into another block of memory. and they won't catch this. The other allocator also has a continuous block of memory, no overflow protection, but fortunately also out of band. The way the allocator is structured is that they try to fill the gaps between the blocks. So if you can overflow one block, you will very likely hit in a block which is allocated. So this actually helps exploitation. For minute, it's the metadata where all the information about the block is inline. So you can do the classic double free exploitation stuff. If you enable debug malloc, they check for double free, which is, yeah, I guess nobody will enable it because it's a debug flag, right? It's not for production. But they don't have any safe unlinking, no guard checks, so they will not be able to detect overflows in the heap in any way. Yeah, they have a CLOC, which has a classical integer overflow, and they even know about it. That's the worst part. In 2002, basically every C library was fixed for this bug. The problem here is that for CLOC you provide an amount and a size, and it allocates the multiplication of amount and size for you of bytes. And if this multiplication gets too big, it will not fit into the result. The number gets truncated, and you will get way less memory than you expected. So you will very likely write to memory that you have not allocated. So yeah, that's an memory override waiting there to happen. But there's another one where they have an overflow using addition. So if you allocate, or if the application tries to allocate a very big chunk of memory, they add the array in a header size. And this might also overflow, and you get way less memory than you expected. This one they apparently don't know about. So yeah, you really have to take care. You really have to take care on how you write your application that people cannot trigger these bugs. But what we learned from years of C experience is that you should check those things in the allocator as well. How is it looking for Riot? There's just one allocator. It's for MSP 430. They have a double free protection, sort of. They don't implement free. So everything you allocate for as long as the device is living. And they also have the same integer overflow in the CLOC. So that's, I told them, but they didn't fix it. So they suffer from the same problem. Zephyr, the project from the Linux Foundation, they also have 2 allocators. This lab has a continuous block of memory, but they also have no hardening whatsoever. They have no double free protections, no guards. So it's basically exploiting like Linux in the 90s, right? So every bug you have will be exploited very easily. The same is for the heap. The heap is for the dynamic sized allocations. Also, the metadata is inline, so you can do the classic double free exploitation. You can overwrite the next chunk. It's bad. Do you notice? If you enable asserts for Zephyr, they actually check the multiplication overflow. I guess asserts are usually sort of similar to debugging, so I'm not sure how many people actually do this. But if you disable the asserts, they also have the overflow. And they have another one in malloc. I guess you remember this or recognize this from the slides before. They also add a block header size to the amount of memory allocate. So if the amount of memory you want to allocate is very big, classical integer overflow, you're screwed. So what do we learn from this? All the allocators I looked at, none of them were hardened. What browser developers are currently doing is they start to bring their own allocators for different use cases and whatnot, which are very, very hard, where they try to make exploitation very, very difficult. The same goes on in the operating systems we are using on the desktop. We learned a lesson the last 20 years that people will find bugs if you write code in C. They will find memory corruption issues, and you have to protect against them and make exploitation harder. The IT world seems to not have learned this lesson yet, which is sad. There are some more bugs. For example, the realloc implementations are sometimes not POSIX compliant. Yeah, take a look at it if you want, or even better, provide patches to improve it. What else is there to attack in IoT operating systems? I guess it always depends on what you're after. Whether you want to root the device to put a new firmware in there, or if you want to just exploit it remotely. I haven't looked at this stuff too much, mainly because I was interested in the operating system itself and not in applications running on top of it. So I never looked at a device which was using one of those operating systems. I did a quick grab in some of them to see how good the code quality is, if it is possible to find a bug in a few minutes. There are some example apps in Contiki, for example. One is a web browser. What you have here is they define a character array with a certain length, and later copy some data into it from the URL. And actually, they check that the data they copy in there is not longer than the array size, but they don't copy it at the beginning of this array, but they copy it at position 5, so it will overflow in the end. In this case, it does not seem exploitable in most cases. They just overwrite data of the website they fetch. So, but yeah, it shows that. I mean, I guess this static analyzer should have found this easily, right? So my takeaway from this issue is that they probably don't really use them. I have two others which I think are interesting because DSN print bugs are something a lot of people don't know about. SNPrintf is a printf which prints into a buffer, and you can give it a size parameter, and it will only print this many characters into the buffer. And the return value of this function is the amount of bytes it would have printed if the buffer was big enough. It's not the amount of bytes it prints, but so if the buffer is too small, and you give it, like the buffer is 10 bytes, and you give it something with 20 bytes, it will return 20. So if you do size calculations based on this return value, for example, like this one, you will run over the end of the buffer. It's no guarantee that you will stay inside the buffer. And this is something, yeah, not a lot of people seems to know about. This is another one in Contiki. Basically the same issue. They don't check if the amount of bytes they printed is larger than the size they have. So they continue printing and possibly overflow the buffer. So what is my conclusion from this? People are still writing popular operating systems in C. There are some projects. There's one where they're using Lua to write an IoT operating systems. There's also one where a person, I guess, is writing one in Rust. But those don't seem to be the popular ones. So people are still having a mindset of, okay, I'm writing an operating system, it has to be in C. None of them seems to be hardened. Okay, you could always argue with the size that if I want to harden stuff, I have to add more bytes and it's getting too big. True, but then make it optional. if the person developing an application for IoT sees, okay, I still have 100 bytes left, hey, let's see, if I turn it on, does it still fit? And then they can have the advantage of being more secure. But not having the code in there at all, that's, yeah, not good. Nearly all of the allocators I looked at were buggy, had classical bugs we should have learned from. I mean, we should learn from past mistakes, right? Otherwise, we can't improve as an industry. And yeah, the randomness infrastructure just is not there. If you take care as an application developer and include a proper random number generator for the hardware, and it's one which can't fail or not fail in a bad way, sure, it's still good. But the operating system itself does not help you do this. Yeah, thanks. That's for me. If you have questions, shoot. Otherwise, I guess I'll be outside for a while. Just come to me and ask me.
Hi, I have 3 questions for you. First is just pardon my lack of knowledge about this field. Are these single stack OSs? Are these single stack OSs? Are these single stack, meaning do you have multiple stack? Do you have a kernel user separation here, or there's no? Okay. So in that case, you are also saying that these OSs don't have an MMU. Is that why they don't have an MMU? Or I mean, if they don't have an MMU, how are they? So is that, I mean, then it perhaps makes sense that not having an MMU, right? Yeah, sure. Yeah, I mean, my question is, since they are single stack, is that the reason they don't have an MMU? Because they are single stack. Because chip don't have an MMU and this OS doesn't care about an MMU, and yes, okay, and okay, that's fine. And then the last thing was a small comment. So in the previous slide, you said that the problem is that they are written in C. We don't have an alternative yet to write an OS, or do we? Okay.
Yeah, I guess you have a lot of alternatives. You can switch to better languages, you can, or more secure languages. You could do some hardening in your operating system. I would go for the more secure language, but yeah. Yeah, true. Sure. Yeah, that's actually an argument I heard from the IoT community. Yeah, we just have a C compiler, so what should we do? Yeah, I mean, the Lua engine, you can compile it with a C compiler, so and embed it into your C code, so then you have everything you need, right? I haven't looked at embedded Lua yet, but I think you can get a Lua engine for a normal desktop like around 5K or something. Okay, it's memory, but having this kind of improved security, I guess it would be worth it. Anybody else?
So, okay. So you said, right, we can actually implement JavaScript runtime into that, right? So, but as per my understanding, IoT devices have to be some certain real-time requirements. And if you add JavaScript engine to it, it will add GC, garbage collector, and then it will have some additional overhead. So what is the trade-off that should be there? I mean, how do you balance that? Anything that you...
I guess you could get Lua to perform in real-time environments. As far as I remember, the allocations in Lua are not done by garbage collector, but by a classic allocator. I'm not sure why they choose to have JavaScript support or support it as a package. Maybe it was just the Riot OS is having a very strong academic focus, and sometimes it's like just people who want to do their masters or bachelors, they write stuff for it and just to see if you can do it. So I'm not sure if anybody actually uses the JavaScript engine for Riot, but it's there. So it at least sometimes it should have worked for someone, right? Yeah, yeah. The question was about the MSP 430 code, where there is no free for the allocator. My suspicion is that they just use the allocator in this case to do some static allocations in the beginning. And then every part or every subsystem has a block of memory it works on. And after this initialization, no part of the applications are supposed to allocate further memory. So I guess it's, I mean, that's something that you actually should do, I guess, if you write IoT. So you don't get into any denial of service issues because you run out of memory or something. But a lot of the code that they pull in from the embedded world is not doing it. So, but as I've shown on the slide in the beginning, too many slides. The operating system is just a small part of the whole infrastructure, right? So yeah. When I looked at the Riot OS, there's an RSN1 parser, for example, which you could use to parse certificates on something or network protocols. The tiny DTLS, I mean, it's a parser for TLS, right? There's CCN Lite, which is also for network protocol. They have tons of bugs due to historical reasons. They're currently doing a rewrite, so I don't want to badmouth them. They actually one of the projects which are currently putting a lot of effort in getting this stuff fixed. So yeah, pick your poison. There's, I mean, it heavily also depends on the application, right? Not every application will use DTLS. So in the end, yeah, you have to see what the specific device you are having in hand is doing with the operating system. So. Yeah. Nobody? Good. Then thanks you for being here and enjoy the rest of the day.